Right, so hello and welcome to Algorithms Live. This week we have a topic which is strongly connected components, continuing the ideas from the previous 2 weeks of this idea of low linking and extracting extra information through DFS. So that's going to be the focus of this episode. We're going to learn how to modify a DFS to extract this information. And we're also going to create a metagraph using that and use it to solve some problems. So it's really just going to be the focus of this algorithm. There are a couple ways you can extract strongly connected components, but I'm going to focus on the ones involving low linking because I think Goncharov and a few of the other methods are well covered in other places. All right, so let's get started. So the first thing I want to talk about is this idea of being strongly connected. So what does it mean to be strongly connected? All right, so this idea is you have a digraph. So unlike the previous weeks, we're actually dealing with directed graphs. And so digraph is just short for directed graph. So there's now an orientation on the edges. And so to be strongly connected, what we say is if you just take all pairs, I and j, you have to make it so that you have these two nodes, I and j, there has to be a path from I to j, and there has to be a path from j to I. And so as long as this exists for every single pair of nodes in your graph, then your graph is strongly connected. So then you introduce this idea of strongly connected components. Which is a lot like the components we saw last week, except on directed graphs. The idea is you partition the vertex set. So you just look at all the vertices you have in the graph. You partition it into subcomponents. And you want these to be as large as possible, but you want each of these to be strongly connected. So you're just going to partition your vertex set this way. You're going to make sure that each of them meet these properties. Just going forward and back. As long as that's good, then we end up having an algorithm. So let's talk about ways you can find these things. And I'm not going to go in depth on the simpler to code ones. I'm just going to mention them. So there's this algorithm, you can just look this up. It's called Warshall's algorithm. It's for transitive closure. You can also think of it as like the unweighted version of Floyd-Warshall's, which is the shortest path algorithm that's well known, but it's just 3 for loops. You do it in V cubed. And so one of the ways you can find strongly connected components if your bounds are really small is you just run transitive closure and then do a for loop over every single thing and just make sure that I can reach j, j can reach I. And the lowest number thing that ends up meeting that property is the first time you find that strongly connected component. It's really easy to code. And I recommend just like coding it a few times because if you don't have big bounds, this is just much easier and less code to write and just nice. You can also do VDFSs. The algorithm is very much the same as this, except instead of doing this V cubed thing, it just V times V plus E. But now you start getting into the algorithms we actually care about. You can actually find all the strongly connected components in E plus V plus E time. So one of them is this Goncharov algorithm I mentioned before. And what that does is it just uses 2 DFSs and extracts strongly connected components that way. But there's these 2 other algorithms that I think are kind of cool. There's Tarjan and then one by Gabo. And the idea is to use stacks instead. And you'll see that a bit later in the episode. And Tarjan's one, it also uses low linking, and it also just uses 1 DFS. So that's kind of the advantage of Tarjan. And it's just kind of this neat, little bit strange algorithm. but it connects very nicely to the undirected DFS approach. And so that's why I think it's worth talking about. So we go back to what we learned in previous weeks, which were the low-linking algorithms. One of the big points of emphasis here were on types of edges that we could explore when we do our DFS. So if you recall, we had several types of edges that were useful. So we have our forward edges. So those are our tree edges. They go forward in our DFS. We actually continue exploring that way. So that's what the forward edges look like. So if I were to run a DFS this way, they're basically everything I would hit an exploration on. And those are our forward edges. And last week, we also had these things called back edges. Something like that. So they're basically, you're currently doing a DFS. It's actually on your call stack of the DFS. You actually have this node. So then you get these back edges. But now, since we have directed graphs, we can also have these things called cross edges. And they cross between components like this. So the last kind is called cross. And something extra we're going to have to deal with in terms of our DFS, something that we're going to have to consider when we're trying to extract these strongly connected components. So let's think about this a little bit and think about some of the properties that exist in terms of doing a DFS on these directed graphs with respect to the strongly connected component. So one thing, if you're doing a DFS, you're going to still get a DFS tree. The neat thing, though, is as soon as you hit a node here, the DFS is going to hit everything in its strongly connected component. Let's say this is the first node you find in the strongly connected component. You have to hit everything in the subtree. And that just follows from the definition that if you're at node I or node J, I has to reach J, J has to reach I. So of course, I'm going to hit everything in the strongly connected component. So that's the first property is once you enter a strongly connected component, you're going to explore all of the strongly connected component right then and there. So everything's all together. And so what I'm going to do is I'm going to call this node that I first hit for the strongly connected component. That's going to be the root of the strongly connected component. So the very first node you hit is called the root of the strongly connected component. And if you look at this in terms of the low linking, so you may have nodes down here, they'll have back edges here, nodes down here, back edges here. They just hit different parts in terms of this DFS. But you'll notice that if I had a low link that passed up here, then I can reach this through forward edges, but I can use my back edge to reach up here and then reach here. This would be in my strongly connected component. So in other words, your low link should never pass the root of the strongly connected component. That's the property. Okay. Another thing you can observe is if you're doing a DFS, you're basically only going to take one forward edge here. And then you're going to hit all of your strongly connected component here, and then maybe have some back edge up here. So in other words, there's only one forward edge. When you're exploring for the strongly connected component. So that's kind of a nice property that we also want to take advantage of here. And the other thing to keep in mind is this edge. So if you're at the root and then you're going to explore your strongly connected component, it's never going to be a back edge that you find your strongly connected component for. Otherwise, that node would have been the root node you're touching. And it's never going to be a cross edge because you would have already found it from these other properties. So that just makes it really easy to know that everything in the subtree that I'm processing right now is basically going to be in my strongly connected component. They're all going to be processed together, except what may happen is a forward edge may leave a strongly connected component, or it might be a cross edge that hits another strongly connected component, something like that. But they're all going to be grouped together conceptually. All right, so let's take a look at a key property here. So after you do this DFS, now one thing to keep in mind is some of these edges may be cross edges to something else. You're not going to have any back edges at the root of the strongly connected component. So that's good to know. But you may have other cross edges. You may have other forward edges as well. So you may end up hitting some other node that's a part of a strongly connected component. So you may have other forward edges, but only one of those forward edges is going to be your strongly connected component. And so the key property for detecting these things, when you're doing your DFS and doing your low linking, is if your low link value at I ends up being the same as your preorder value, then that'll be true if and only if you're the root. So that's the idea. So we'll be at some node I, we'll be exploring some node J, we'll run through this entire subtree right here, and maybe somewhere in the subtree we get a back edge going back up the tree, up to node I, and then we'll end up having a strongly connected component that way. So now we actually have to extract them because the strongly connected components are a subset of the vertex set. And we ran into a kind of similar problem when we were doing SCCs. Or the similar problem was articulation points. Because remember, articulation points were good for finding two vertex connected components and two vertex connected components. So our problem is very similar to that in terms of pulling out. In this case, we were pulling out edges off of an undirected graph. And the way we got around that in that last video or 2 videos ago was to use a stack. Just kind of intuitively, things are going to be grouped together. And then we can remove things off the stack until we end up hitting our root. So what we'll do is we'll just explore down here, detect that we're the root of the strongly connected component, pop things off the stack as we go, and then eventually we end up, we'll find everything. We also know that forward edges may detect other strongly connected components later. So the idea is we handle those using the stack method first. Those will be gone from our stack before exploring the one that we're rooted with at I. And you can prove that property if you'd like. So the only thing we have to worry about here, so low linking involves back edges. Low linking involves forward edges too, because we have to do subtree aggregates. So we need to, every time we explore forward edge, we aggregate all the low links. And then every time we get a back edge, we update what that low linking value is. But we need to find a way to ignore cross edges. They're going to be a problem. Because if we end up having a cross edge here, the way we're doing our low linking, if we're doing it off preorder numbers, this is going to have a much smaller preorder number than anything on the call stack coming down to me. So this is in a different subtree entirely, and this is going to have a smaller preorder number than anything over here. So the idea is we want to just ignore cross edges, and I'll keep that as an implementation detail for now. Yeah, actually, I'll go explore it. What I basically do is, as I find strongly connected components, I basically know that low link value is no longer relevant because I've explored everything in that subtree. So I just overwrite my low linking value with a really big number before I leave. And that's how I'm going to ignore cross edges. It's a very elegant way to ignore cross edges. you can also keep some kind of flag saying, I've already explored this, or some kind of flag saying, am I on the call stack? And that'll tell you if it's a back edge or a cross edge, and you could ignore the cross edge that way. So there's a couple ways you can do it implementation detail wise, but I like just overwrite the low link value, and I just make it the size of the graph. I'm going to mark it here when I do this example using infinity, but I'll use the graph size as that value when I actually go implement this thing. Okay, so let's run through an example of finding strongly connected components by hand so you can see this. And then we'll go code it and talk about a problem that I think is kind of neat. All right, so I will draw a graph here. And feel free to ask questions in the live chat as things come up. Something like that. And something like this. Okay, maybe I'll set that over. And so I'll put the strongly connected components over here as I find them. And then I'll just start doing a sort of DFS here. So I'm going to start at node 1. Keep in mind, I could have started at any node in this graph if I'm doing my strongly connected component search. So if I start over here, I'll DFS everything I haven't seen, and then I'll have to do another DFS to something else. So you're not always going to explore everything by hitting the first node you see. So in this graph, I'm just going to DFS starting from here, hit everything, but you might have to explore multiple times. Okay, so I start here. I'll be at node 1. I'll go to node 2 and then node 3. So 1 goes to 2, goes to 3. And then I need to store information on preorder numbers. So 1, 2, and 3. And I'll keep my low link value to be exactly the same. So on the left, I have my preorder number. On my right, I have my low link value. So I'm doing this DFS down. Just to make things a little more complicated, let me go to node 5 first. So I'll hit node 5. And so I get to 4, 4. And then from node 5, I'll go to node 9, 5, 5, something like that. So I've explored the whole subtree there. And as I'm doing my DFS, I need to maintain a stack. So here's my stack right here. So I'll just be pushing 1, 2, 3, 5, and 9 onto the stack. So I've explored all of node 9 in terms of this. So when I hit node 9, the very first thing that happens is node 9 gets lost from the stack because its preorder value and its low link value are the same, and I'm done exploring it. So in that case, I'll call this node 1 in my meta graph. So strongly connected component 1 is going to just be node 9. I pop that off the graph like so. So I pop back to 5. And 5 is also done because it doesn't have any nodes to explore. No neighboring nodes to explore. So I also pop that off the stack. And it's my second strongly connected component is node 5. Okay. So then I come back here. I have stuff left to explore. I need to explore node 4. So 4 goes onto the stack. And I start exploring 4 this way. So 4 is 6, 6. But then 4 ends up exploring to 5. And so we start seeing our first cross edge. And so you can see this problem. If I update my low link value to be 4 here, it's actually will destroy things because 4 is actually a root of its strongly connected component. So that's another thing. When I pull things off, I just mark these as infinity. And now if I take the min of this infinity and this value here for the low link, it ends up being destructive and everything stays the same. So I basically resolve that problem of having this cross edge, and I don't have any problems with this cross edge. Okay, so that's this edge I'm exploring from node 4. So now I go to node 6, over out to the right. So I get 7 and 7 in terms of its cross edge. So 7 goes to 8. So it goes 6, 7. So it's 8, 8. And then I go out to node 8. So I get 9, 9 this way. But I end up getting a back edge now. So my back edge comes up this way. So I update my low link values to 7. And then I also get a cross edge going to node 9, but I preserve the 7 in terms of that back edge that way. So I update that to 7. This is a forward edge, so I also update off the low link value. I need to store that subtree aggregate. I need to know for this entire subtree what's the highest I got to. So I change that to be 7. And so I get 7s this way, and I found another root of my strongly connected component. Every time I enter a node, that's when I push things onto the stack. So I've been a little bit bad, haven't been doing that. So I push those onto the stack. Now I've hit the root of my strongly connected component. So I'm going to keep popping them off until I find this node 6. So 6, 7, 8 is my next strongly connected component. So I pop those off the stack. I get to node 4. It also meets the criteria of being the root of the strongly connected component. So I pop that off the stack. Okay. And then node 3 still has an edge to explore. It goes up to 1 in the strongly connected component. So I get a back edge here. Update this to 1, 1. And so you'll notice it doesn't meet the criteria of being strongly connected component. I get to the root, pull everything off the stack now. That's my last strongly connected component. And that's how you run the algorithm. So you should try building a graph and then running the algorithm by hand and seeing how things go. Okay, so that's the algorithm for Tarjan's, how you run this low linking algorithm and actually extract the strongly connected components. The other thing when you do strongly connected components like this is you end up getting something called a metagraph. And it's based off of these strongly connected components. They become new nodes in your metagraph. So what we'll do is we'll just group things together based on the strongly connected components. So node 9 here ends up being its own component. Node 5, node 4, this group here, and this group here. Those become nodes in our metagraph, and we just label them by the number that you see here. So we get a 1 here, a 2 here. So you just relabel things, a 3 here, 4 here, and a 5. So I want to point out something in terms of the order that these things are found. You'll notice that if I go through these components in order from 1 to 5, in order this way, this gives me a topological order of this metagraph. So let's talk a little bit about the metagraph in general too. There's a few things I want to point out about the metagraph and how to build it. So first off, it is a DAG, so it's a directed acyclic graph. This makes sense because the strongly connected components, when you compress them, they get rid of the cycles. So if you have a cycle, then all the nodes in the cycle are going to be in the same strongly connected component. That's the thinking there. So when you build your metagraph, you do get a directed acyclic graph, and you look at these nodes in order, they'll be in reverse topological order using this algorithm. This is pretty handy because a lot of times what you'll do is you want to do something like dynamic programming on this metagraph because it is a directed acyclic graph. you don't have to do a recursive DFS to do that. You can just run through iteratively through these nodes in order, and you can typically solve things with some iterative dynamic programming and solve that problem. There are a lot of problems where you end up with a subproblem, then you have to go build the metagraph and then solve some problem. And I see a lot of people when they learn strongly connected components, they say, oh, I have a DAG, let me run a top sort algorithm on this directed acyclic graph, and it's completely not necessary. You can just run through these components in order, which is pretty cool. So I'll just redraw things conceptually. So if I look at my graph here, the metagraph is just grouping together each of these nodes. And so we end up with something like this. And so you get rid of all the edges that are within the component. And so you're just grouping together all these nodes, and you stop caring about how they're interconnected within the component when you form your metagraph. And so the edges that you end up adding in terms of this metagraph are basically anytime the label of what your strongly connected component is. So you usually keep an ID table for this. If it crosses the two components, then you know that you should add an edge to this strongly connected component, like this. So it crosses between the two. And so the big thing I want to say here about building these metagraphs is beware of parallel arcs. So a parallel arc is, or parallel edge, is if you end up having two edges like this. So one thing I like to do in problems when I'm doing strongly connected component problems, or I write them, is I like to guarantee that there are no parallel edges in the original graph. But that does not mean that you can build a graph such that the metagraph has parallel edges. It's fairly easy to do. So here's an example of one such graph. And just build something like this. And so if you're not really careful, the metagraph will look something like this. You group those two things together. So whatever this meta node is, so we'll call it 1, or it would be 1 and then 2. You end up with two parallel edges like that. And so this can, depending on the problem you have, could actually break things for you. You could, having that parallel arc could cause problems. So something to consider, and if you're doing a problem involving strongly connected components, making a test case like this and just testing it before you submit is a really good idea. Okay. So that's our first, that's basically how the algorithm works. So I want to talk about kind of two cool problems now involving strongly connected components before we start coding this. Actually, I think what I'm going to do is I'm going to code the strongly connected components algorithm now, just so you can see it implemented in Java. And then I'm going to discuss two problems. So the first thing I'm going to do is just get the code working. Then we're going to discuss a problem and then use the code that I write for this to solve that problem. And so in the blog, I mentioned this problem called proving equivalences. That's the problem we're going to be solving. And then I have a second problem that wasn't in the blog that I think is just good to discuss, but I won't be coding that one. I do want to just write the code for strongly connected components right now, and then just kind of go over how this stuff works. And I do want to also test it. So that would be good before we solve this problem. Now let's do that. As you can see, actually, there's this thing called Bash for Windows now, and it's really great. So now I can finally code things in Bash on Windows and not use the Windows terminal. So trying something new out, but it's messed with my color scheme. So this could be better or worse. I haven't quite decided. Okay, so The way I typically code this, if I'm doing a graph problem, is usually make a graph class, and then I make a class for the algorithm. So I'm going to just call this one Tarjan, but it's really the Tarjan SCC algorithm or something. And I'll make a class called Kotaraju and kind of do it that way. And the idea is I make a graph class so I can pass it around to different algorithms. So if I'm making metagraphs, this is a really good idea. So that way I don't have to make adjacency lists and populate them for every single graph I'm having, or problems that have multiple graphs. That's typically what I do. So this is the graph. I'll make a graph class and pass things around. And I'll add an add edge function because that sounds like a good idea to me. Okay. The other thing I'm going to do is just read in my graph right here because it just seems like a good idea. So the way this problem works is you're given some number of test cases. So I have my test case template here. And then you're given some number of edges. So I have my edge. Just going to loop through all the edges real quick and populate this graph. Okay. So let's talk about the Tarjan SCC algorithm. So the way I typically code this is I just make a constructor and then do all the work in the constructor. So I save my graph like that. So we do need to store some information. So the way this is going to work is I'm going to have my pre-order numbers. So this is both the pre-order numbers of the node, but it's also going to double as a visited array. So if it's unmarked, then I know that it hasn't been visited yet, and I have a forward edge. I'm also going to keep an ID array. So the ID array basically tells me for this node what strongly connected component I am in. Usually this is the best way to save strongly connected components and to build metagraphs and stuff like that. So I'm also going to store my lowlink array. So it just stores my lowlinking value for this entire subtree. And let's get... We also need a stack for our nodes. So that's what's here is a stack. And then we'll need a pre-order counter. Storing like what pre-order number we're currently on. And the last thing is I like to keep track of the number of strongly connected components. And the number of strongly connected components is also the size of our metagraph if we want to build the metagraph later. And so that's the pieces there. So I need to stack, make my pre-order numbers. And so the ID and low link value are both the same size, so that's fine. So we start off with 0 SCCs. I'm going to make everything 0 index for the pre-order counter. And then before I do my DFS, start it at -1. Okay, so now I can start coding my DFS. This one, I don't need to keep track of a parent. For the directed graph, it becomes really easy just to keep track of where I am node I. And then to kick off this DFS, what I'll do is I'll loop through all the nodes. And if I haven't seen this node before, I can do a DFS from node I. So this prevents that case where I didn't start at a node that can reach everything else. Your graph could still be disconnected, and this just handles all of that. Okay, let's talk about this. So what I'll do is I'll just save my pre-order number using the pre-order counter. So initially, my low link value is exactly the same as the pre-order number. That may change depending on how I explore my subtree and then look back up. And I also have to push my node onto the stack. That's useful. So now I loop through everything that's next to me. And so this is basically the forward edge case. I should probably change my colors at some point, because that comment is very dark. But this case right here is the case where I have a forward edge going forward. And what I'm left with here is this is for forward, back edge, and cross edge. And it turns out in all those cases, I always want to update my low link value off the low link value. So this becomes a little simpler to implement than the undirected case. I just save. So if it's a back edge, I can update just off the low link value, and that'll be fine. If it's a cross edge, I'm going to sanitize these low link values anyway and get rid of them. So that way the cross edge just returns a big value here if this happens to be a cross edge. And if it's a forward edge, I need to do the subtree aggregate. I have to make sure my subtree, I have the lowest low link that all the forward edges can reach. Okay. And so then if my low link value is the same as my pre-order value, are we the root? That's basically what this tests. And now I can start pulling things off my stack and finding if they're in the strongly connected component. So I'll do that this way with a horrible looking while true loop, but it turns out I think this is the cleanest way to implement this. So I just keep popping things off my stack, set the thing equal to the current counter for the SCC. So num SCCs is actually a strongly connected components counter. And then I update the low link value for this node to be something really large. So I choose the graph size because that's bigger than any pre-order number I'm going to have in my whole graph. So it makes a nice infinity value for implementation. And then so I know to quit when I'm pulling myself off the stack. That's why I do the break. If you don't do this in this kind of a loop, you could probably do some Boolean flag stuff and things, but I typically code it this way if I'm doing competitive programming. It just makes it easier to code, and that's what matters here. And then I just increment. This is a new strongly connected component. So I'm pulling them all off the stack. Let's run through the code again. So you just push, when you explore this node, you push it onto the stack, set up your pre-order number and low link value. Every time you explore an edge, if you haven't seen it before, you explore it, update your low link value on the post order side. And then once you're done with the entire search of everything, you can detect if you were the root of the strongly connected component because you know you won't get any higher up the graph, up the DFS tree. And then you can pull yourself off. Pull everything off the stack until you hit your node. So any deeper strongly connected components down the tree will been popped off before you get here. And so that gets handled very nicely, and you just label things correctly. Okay, so that's the strongly connected components algorithm. I'm not confident I coded this correctly first try. So one thing I'm going to do is I'm just going to test this. Very easy to test. I'm not going to do this in any efficient way, but you could probably code this a little more efficiently. It's just for my own testing. I'm just going to loop through the strongly connected component labels. So that goes from 0 to strongly connected components -1. And I'm just going to write a little printout of the current node, current component, and then just loop through all the nodes. and then I can group them by strongly connected component. This is easy to do efficiently. You could just make an array list of each component size and then just put them in the right bucket. But it's not like I have to do anything fancy to pull this information out. That's my strongly connected component here. Just going to print that information out. So if you took notes going through, I'm just going to, the test graph that I ran by hand, that's the graph I'm going to build here. scc.id. Oh, right. I should call Tarjan. So what I typically do is I just call my strongly connected component class to be this. So I should define it. Okay. So let's make the graph. There's one test case. There's 9 nodes, 12 edges. So 1 goes to 2, 2 goes to 3, 3 goes to 1, 3 goes to 4, 3 goes to 5, 4 goes to 5, 4 goes to 6, 6 goes to 7, 7 goes to 8, 8 goes to 7, 5 goes to 9, and 8 goes to 9. That's my graph. So I just drew out my graph like this. And it is not working. Let's see. Let's see if I can find out why. We also make this labeled like that. So this looks correct to me. My pre-order numbers, push things onto the stack. Take of those two. Let's reset. Huh. Works correctly there. So maybe it was working correctly. And it was just my terminal. Nope, something's still wrong. So 6, 6, 8, 7, 8, and 6 should all be different here. I think I want to make this H2. Boost 1. This should, yeah, I typed in my graph wrong. That's why. And so as you can see, this was kind of the strongly connected components we wrote out in the example. The exact labeling, I think, is actually the same too. That's not always the case. It could go in a different order than I did my DFS, but it seems like we got the exact same labelings as we did by hand here. It's good in terms of code. The real test will be running it on the graph going forward. Okay, so I'll also type in the samples from the problem that we're going to be solving, and then we're going to talk about this problem of equivalences. So let's do that now. So I wrote So we have this problem called proving equivalences. So you can go look this up on Caddis. It's just equivalences. And let's talk about what this problem is asking and how to solve it. Okay, so this problem is actually well-studied problem. There's a few papers on it. It's called strong, maybe smaller. It's called strong connectivity augmentation problem. So boiling it down to its base elements, what we have here is we have a graph. And what we want to do is we want to add the minimum number of edges to the graph to make that graph strongly connected. So originally, it's not strongly connected in any way, but we'd like to just add the minimum number of edges. So give you a small example here. So let's say we take this graph right here. Then the minimum number of edges is you just add this edge right here. That's 1. Now we have a strongly connected graph. It doesn't even have to be connected. So we could have something like this and something like this. And so what we'd have to do in this case is add an edge here, and then add an edge here, and now it's strongly connected. So the answer here would be 2. There, you could do it suboptimally. So there might be something tricky here. So maybe we add one here, add one here, add one here, maybe add one here. Yeah, something like this, and then add one here. So you can see I added 4 edges. Maybe I should draw them in blue. 6. Something like that. And we basically just want to make sure for every pair ij, I gets to j, j gets to I. That's our goal. But in this case, you can also do it in just 3. So I could add this edge here, add this one here, maybe add this one over here, and 3 would be sufficient here. Okay, so let's talk about how we attack this problem. So step 1 is the graph's not necessarily acyclic, but just to make the problem easier, I can compress the graph to a directed acyclic graph. So it's an SCC metagraph. And then step 2 is now I just solve it on the DAG. And just add appropriate edges anywhere in the SCC, we end up getting the same problem. So what I'm going to focus on is this DAG version of the problem. So I'm going to assume initially the first step I did is I just compressed the graph to SCCs, and that's how I'm attacking the problem. So there's a nice paper on how to solve this that was written by Tarjan, and I forget the other person's name. It's like S. Warren. It's actually, they came up with a way of doing this, of extracting, oh, maybe I don't do that yet. But extracting the minimum number of edges to draw, and it turns out their algorithm is wrong. And so there's a later paper that shows it's actually wrong, and it gives a counterexample and then shows how to fix it. So there's a nice thing you can look up a bit later on how to solve this. But I just want to point out something here is how you connect things actually matters. So if let's not talk about that yet. Let's move this over here. Okay, so let's talk some terminology here. So we have a directed acyclic graph. We're going to call something a source if it has n degree of 0. And we're going to call something a sink if it has out degree of 0. Okay? And you'll see that these right here, these are sources. I'll put the plus sign next to them. And these right here, these are sinks. I'll put the minus sign next to them. So those nodes are sources. Those nodes are sinks. And the thing I want to point out is you don't actually have to connect anything but sources and sinks to get this to work, because everything that can reach here can reach internal nodes, and those internal nodes could reach other sinks. I guess it's not too obvious. Maybe it's just intuitive. But that's the first observation, is maybe only dealing with the sources and sinks is a good idea. It's actually fairly tricky to prove. So what I'll do is I'll call S the set of all sources, and I'll call T the set of all sinks. So kind of flow notation there. And it's fairly obvious if you start playing with this a little bit that you need at least this many edges. So the max of S and T edges. So you don't, you can't do less than this. And the reasoning here isn't very hard. Just take any edge from the sink, and it needs to be able to reach all nodes. And in order to reach all nodes, well, you're going to need at least one edge. Let's do another one. So let's say we can say the same thing in the source. It must be reached by all nodes. So you need at least one edge. So the idea would be to connect edges from the sink to the source. You can kind of share edges, but if you have an imbalance of source and sink, then you need a little bit more for the bigger of the two. But you'll see that how you connect these things actually matters here. So I drew them in this way. 1 can't reach 7, 7 can't reach 1 in this graph, so it's not strongly connected. But if I just change things ever so slightly, take node 3, hook it up to 7, take node 6, hook it up to 1, then I get things to work. So we know we need at least this many edges, but is it sufficient? And it turns out, yes, that's the case. It's sufficient. You're always going to be able to do this. It's always, you just take this many edges. You'll always be able to hook up your sources and sinks appropriately so that it's always strongly connected. And the thing I want to say about it being sufficient is this is really hard to show. I might do a separate video on just like how to show this. Well, maybe hard's a strong word, but it's harder. It's definitely not elegant or trivial to show. And it's also a little bit hard to find. There's a little bit of work to do there, and that original Tarjan paper is wrong. But what you can do is you can read this other paper. It's called A Note on Ezran, and so I'll write out Ezran's name. A Note on Ezran and Tarjan's algorithm for strongly connected It says, a note on Ezrin's and Tarjan's algorithm for the strong connectivity augmentation problem. So if you look up that paper, this Ezrin-Tarjan paper, not the original paper, but the revision, and the guy who did the revision's name is Raghavan. So that's the author of the revision. You can actually see that you can do this entire thing in V plus E time. You can actually extract those edges. But one nice thing about this proving equivalences problem is we don't actually have to extract these edges. We just have to find the max of these two values. So that's all I'm going to do to solve this problem and hopefully get it correct. So I'm going to go finish off my code for this. And there's somewhat of a special case here. If the graph is already strongly connected, you don't have to do anything special. So I don't have to add any edges. But in that case, my metagraph node will be both a source and a sink, so it's really easy to detect. So let's get rid of some of this code here and solve the problem. So what I need to do is I just need to figure out degrees and in degrees of all my meta nodes. So I don't have to actually build the metagraph in this problem. I can just do it this way. And then I'll talk about how you build the metagraph a bit after I code this. I think that's useful information. Or maybe show you some code for if you need to construct the metagraph, how you would do that. So the idea here is it's only an edge in the metagraph if it traverses a strongly connected component. So that's why I check here. And then I'll just save information from the out degree and in degree. It's important I also use the ID from the table because this tells me what node I am in the metagraph, this table right here. So I just do those two things. The in degree is coming off of node J. So it's leaving node I, going into node J. So I just find the strongly connected component and save that information. So now I need to also know the number of sources and the number of sinks. So I can just code it this way. Loop through all the strongly connected components. And that's my answer. I literally just count things that have in degree 0, out degree 0. And so if it's an isolated node all the way by itself, it'll be present in both counts, so it doesn't affect anything. And it also works. So let's test it on the samples in our own case. So in the hand-drawn case, so the samples, it comes out like this. In the hand-drawn case, we just had one strongly connected component, so it should come out OK. Some debug print statement somewhere. Now stack information. Make sure it works on samples. Okay, so let's go submit this and see if we can get it correct. And you see, get accepted on this problem. All right, so code appears to be working. One of the things I want to talk about is how you actually extract the metagraph now. So let's say instead of figuring out this information, I actually have to build a new metagraph. This is why I make that graph class. So I'll show you the code for that real quick. So I just make a new graph called meta, and I save the number of strongly connected components. And then I just do the same double for loop here. And instead of storing this information, I just now add an edge for meta. And so what this is going to do is actually going to allow parallel arcs, the way this is coded. So if you want it to not allow parallel arcs, one thing you could do is modify your graph to have tree sets here instead of array lists. Or sometimes what I'll do is I'll just write a function called simplify. And then it just creates a new graph and erases all the duplicates in every single adjacency list. And that's fairly easy to do. And then just returns a new graph with no duplicate parallel arcs. So that's typically how I code that sort of thing. And so I do have one more problem I could show, but I think the episode's already run a bit long. So I think I'm going to skip that one this week. But you typically want to find a problem where you actually have to build this metagraph and do something for it. And I'm not sure I had one in the blog, but if any of the viewers, if you have a good problem for strongly connected components, please leave it in the comments. I'll add it to the blog post, and I'm sure everyone will benefit from it. So that's all I have for this week for Algorithms Live. I hope you all enjoyed this episode. I'm thinking for next week, I want to cover something related to strongly connected components. So I'm thinking 2SAT. I know a lot of people really like 2SAT, and it's got some really neat problems. So I'll try to find a few good 2SAT problems, and I think that'll be next week's episode. And as always, if you find something that you want me to go over, I'll be happy to add it to the list. I got numerous requests for suffix arrays, so I think those are going to be coming soon. So thanks for tuning in this week, everyone, and see you guys next week.